So, in our last two classes, we have already discussed some very basic ideas about the quantum field theory, right? Now, we discussed about the principle of least action, and then we obtained the equation of motion. Then we talked about Lagrangian density, fields, then field theory, both classical field theory as well as quantum field theory. We also discussed few drawbacks of non-relativistic quantum mechanics, and then the relation between particle and field. We also discussed about first and second quantization and why we don't need any third quantization. And today, these are the topics which we will talk about. Now, the first thing, if you remember, we started with the action principle. And so I thought maybe we do need to put some more time on the importance of the action principle, both in classical and quantum mechanics. So, you see, you also know these facts. In classical mechanics, we have two equivalent formulations, one based on Newton's equation of motion, which you have done from your high schools, I think. Class 11 onwards, you have solved various types of problems using Newton's equations of motion. And other formulation is based on the action principle. Now, at first, these two formalisms, you might think, or you could have thought previously, that there is hardly anything common between them. Why? The reason being that the first depends on iterating infinitesimal changes sequentially along a particle's path, whereas the second formalism depends on evaluating all possible paths between 2 points and selecting out the one with the minimum action. Okay. Now, you have also seen this proof of equivalence between the equation of motion and the action principle, probably in your graduation third year. And it was indeed a great achievement for classical mechanics, where it was demonstrated that the Newton's equations of motion were equivalent to minimizing the action over the set of all possible paths. Now, so far we are talking about classical mechanics. Now let us go to the quantum regime. Okay. So when we generalize our results to the quantum realm, what happens? You see, this equivalence breaks down. And why is it so? The Heisenberg's uncertainty principle, of course you know this, about this principle. This principle forces us to introduce probabilities, and then we have to consider all possible paths taken by the particle, with the classical path simply being the most likely one. So previously we have only the classical path. Now we have several possible paths, with the classical being the most likely one. So quantum mechanically, we know that there is a finite probability for a particle to deviate from its classical equation of motion. And this deviation from the classical path is very small, on a scale determined by Planck's constant. However small it could be, but we have to remember that on the subatomic scale, this deviation becomes the dominant aspect of a particle's motion. And in the microcosm, motions that are in fact forbidden classically determine the primary characteristics of the atom. We know about these facts. I'm just telling you, recapitulating you the basics. Now, for example, the stability of the atom, the emission and absorption spectrum, right? You see the radioactive decay, quantum mechanical tunneling. What are these? These are all manifestations of the quantum behavior which deviate from the Newton's classical equations of motion. However, it is important to note that even though Newtonian mechanics fails within the subatomic realm, it is possible to generalize the action principle to incorporate these quantum probabilities. In this way, the action principle then becomes the only framework to calculate the probability of a particle. Sorry, what do you calculate? To calculate the probability of what? Of a particle, how much it will deviate from its classical path. Okay, so in a way, the action principle is being elevated into a new foundation of the new mechanics. So what I am trying to stress is that compared to even Newtonian mechanics, which was equal to the action principle in classical mechanics, in the quantum regime, it becomes the single most dominant, important formulation of the mechanics. Okay. Any questions?
No, sir.
Okay. Now this was just information for you to remember, because in quantum field theory, when we start, we use this action principle, and then we talk about the Euler's equations of motion, Lagrangian density, and so on and so forth. So it is important to talk about the action principle. Okay. Now the second thing, this is quite common, and you do know, but how does quantum mechanics differ from classical mechanics? Now, why did I ask these things? Because if I remember, Partho asked me in one of the last lectures, he asked me, why is there quantization or so? And then I told him, if you'll remember, Arundhati was also asking me probably, that certain quantities, say for example, energy, momentum, they have discrete values. And this is the very basic feature of quantization, first quantization. Now, when we were studying classical mechanics, did we ever say anywhere at any place that these quantities, energy, momentum, okay, angular momentum, and so on, they will be quantized? No, we never said those things. They were continuous. But only in the quantum regime, we specifically saw in the black body radiations interpretation, Planck's hypothesis, that only through the quantization, physics could be saved. We can get a meaning out of it. So, the first difference of quantum mechanics with that of classical mechanics is in terms of quantization. Okay. And the second difference is that of wave particle duality. To stress on the fact that a particle can have both the properties of wave as well as particle, wavicle. Also, another interesting feature which is common, which is very particular to quantum mechanics, is the uncertainty principle. And as a result, what it does, it sets limits to the precision with which quantities can be known. Of course, quantum mechanics did have certain limitations, several drawbacks, which we talked about. Okay. And those led to the development of the field and thereafter quantum field theory. But again, quantum field theory also has certain limitations. I did not talk about it last day, but let me just mention to you three particular limitations of quantum field theory. So someone might ask you, okay, you have learned about quantum field theory in your master's degree and so on and so forth. It can explain almost everything in the world. Can you just mention to me three particular drawbacks of quantum field theory? That means three particular things which quantum field theory could not explain properly. Well, one thing we do know is that QFT is having problems with quantizing gravity. We don't have a quantum field theory of gravity because there are problems with the quantization of the gravity. Also, the quantum chromodynamics, it cannot be entirely solved. We have to use perturbations, approximations, and so on and so forth. And the third very interesting, important limitation is that QFT cannot explain the cosmological constant of the universe. Now, probably this we have learned in your cosmology. Oh no, it's another special paper, I think. Okay, you can do a search yourself. It is yet another very important constant of this universe. And unfortunately, quantum field theory cannot explain this cosmological constant. And these limitations particularly led to the development of string theory, motivated the development of a new theory called the string theory. Now, I am not going into the details of the. So, if you can draw a Venn diagram, then in the very center there will be classical mechanics circle, and then outside it will be the quantum mechanics, then outside it will be another circle of quantum field theory followed by string theory. But again, string theory has not been completely experimentally verified as of now, so there is a lot of dilemma in this. Okay, so any more questions till now? Poshali, Partho, anyone, any questions?
No, sir.
Sumanto?
That's it.
Okay. Now, we discussed about several drawbacks of quantum mechanics in our previous lecture. Okay, now let me talk about some more drawbacks. Say, for example, what happens when we extrapolate the non-relativistic quantum mechanics to relativistic case for a free particle. Now, this you have learned in your third semester. I'm just recapitulating the entire mathematics. Not, I'm just telling you the various problems associated with that. Well, of course, this led to various inconsistencies. Now, what was the first inconsistency? Well, the Klein-Gordon equation for a spin zero free particle. This led to, right? The extrapolation of non-relativistic quantum mechanics to a relativistic case for a free particle. This led to what? The Klein-Gordon equation for a spin zero free particle. However, what we observe is that its probability density is not positive definite, thereby preventing the probability interpretation. Next, what about spin half free particles? For them, we have the Dirac equation. Okay. However, this Dirac equation predicted the existence of negative energy states, which implied that matter was unstable. Now, not only that, but also there are three unusual features of the negative energy states. Now, this I am just telling you, but you also probably know. And if not, then you must remember this unusual features. The first one is that the hydrogen atom spectrum obtained from the Dirac equation has no ground state. Okay, now this is absolutely wrong. So this means there is a problem with the theory. Also, the expectation value of position of a free particle displays rapid oscillatory motion. And we have the Klein paradox as well. And what does it say? Basically, for a certain range of incident energy, the amplitude of the reflective wave from a step potential is larger than the incident wave. So, these are the three particular unusual features. Also, we have something very interesting. Well, in the correspondence limit of H cross tending to 0, the non-relativistic Schrodinger equation reduces to classical mechanics, but not to the relativistic equation. You also must remember this. Okay. So we talked about a lot of drawbacks of quantum mechanics. Now, let me tell you what happens, how we do this subconsciously. We have been doing this, but let me just point it out. You see, during the interaction of an electromagnetic field with a system, what happens? We treat the system as quantum mechanical, but the field as classical. Again, we treat the absorption and emission of radiation as absorption and emission of photons, where the number of particles change. So again, there is a lot of inconsistencies involved. Okay. Now, in certain processes, this I mentioned last time, the initial and final states contain same particles, whereas in the intermediate states, there is creation or annihilation of other particles. Now, the final results, of course, depend on these intermediate states. That means how many particles were created or annihilated. But again, our quantum mechanics cannot help us in this matter. This is what I was meaning when I said vacuum fluctuations. Well, you see, at very short distances, much lower than the Compton wavelength of a particle, even when there is not enough energy for creation of particle-antiparticle pair, the multi-particle states due to one or more pairs being created appear due to uncertainty relation. Now we have discussed these things. So what's the problem? The problem is that there is no general way in single particle quantum mechanics to describe such effects. Okay. So, any questions till now? অরুন্ধতী, পৌশালী, পার্থ?
না স্যার, কোনো সমস্যা নেই।
Some things maybe are quite new, probably, but most of the things are common to you, I think. Now, let me talk about the next thing. I discussed this fact somewhat in the last lecture. And what is it? Well, the question is basically why all particles of the same type are the same. What I mean to ask is that are a particle's properties self determined, or are they determined by the properties of its fields? Well, the most important properties of a quantum field are its mass, spin, and the various symmetries that it follows or that it obeys, basically. The particles associated with a particular field have the same mass and spin as the field, okay, and their charges are limited to those that are allowed by the field symmetries. We cannot deviate from that. Thus, for example, let me give you a very simple example. Say for the electron field, what happens? The electron field has a mass me, 511 keV, okay, and spin half. So this means that all electrons and positrons, no matter where they are in the universe, no matter when they were created, one being created right now or another being created billions of years back, no matter what time they were created, they all must have the same mass and the spin. Similarly, since the electron field obeys a certain type of symmetry, the electron charges of its associated particles are limited to either -1 for electron and +1 for positron. But remember that other properties of particles such as energy, momentum are in principle independent of their associated fields, and so they can change. Okay, good. Now, let me talk about the effect of Lorentz invariance on the fields. You remember when I was talking about the Lagrangian? So we talked about the fact that we need to make a theory Lorentz invariant. Well, the requirement of Lorentz invariance gives fields remarkable properties which are not possessed by any mechanical system. How? Well, you see, since the theory has to be invariant under arbitrary space-time displacements, the fields cannot have any atomic structure but must be continuous. Furthermore, the field must fill all space and time, and it has to last forever, everywhere, and can never be removed. So, this partially answers your question. I think Parthu was asking me last time, why is it field everywhere? Why does it needs to be continuous? Well, you see, Lorentz invariance, this in fact is making it so. Otherwise, we cannot have a Lorentz invariance theory. So, our space is spanned by the continuous background of the fields of elementary particles. Okay. Now, I think there are no more questions. So, okay, fine. Now, let me talk about a very interesting topic. And what is that? Suppose someone asks you, well, how is the wave particle duality paradox resolved in quantum field theory? Then what do you say? Well, you can say, come on, in quantum field theory, there are no particles, there are only fields. And in quantum field theory, Schrodinger equation does not describe a probability. It describes the intensity of a field and fields can oscillate, and this oscillation manifests as waves that then cause the interference effects. The particle like behavior of the fields. So, how do you explain that? Basically, this particle like behavior of the fields is explained by the fact that each quantum maintains its own identity and acts as a unit, no matter how spread out it may be. If it is absorbed by an atom, all its energy is deposited into that atom. This is called field collapse. Okay. While field collapse is not described by quantum field theory, there is nothing inconsistent or paradoxical about it. So, the electron is truly a field that exists all of space, and the excitation of electron field is the region where the probability of electron. Okay, very interesting. Probably also enjoyed this discussion. Now, again, if I ask you, how does quantum field theory explain the uncertainty principle? Then again, you can proceed in the similar fashion. You can say that, well, in quantum field theory, there are no particles, no certain or uncertain discussion. Instead, there are blobs of field that are spread out over space. Spreading out is something that only a field can do. A particle cannot do it. So, the uncertainty principle is not much different from Fourier's theorem that relates the spatial spread of any wave to the spread of its wavelength. Okay, any questions, students? I think you are quite enjoying. Poshali, Shumanto, any question? Partho?
না স্যার ঠিক আছে স্যার
ঠিক আছে. Are these things new to you? Or probably you have...
কিছু কিছু জিনিস তো নতুন তো স্যার
আচ্ছা আচ্ছা. No, that's why I'm just recapitulating overall. Because often we get some of the glimpse of the topics in master's degree also. Most of the time you do the mathematics without properly knowing the basic reason, or some of the times knowing the importance of a mathematical result. So that's why I'm just stressing these facts. Now again, let me ask you a very interesting question. So what can you say if I ask you that, does a collection of particles, this one, the second last question, does a collection of particles, say for example, a chemical compound, or come on, you or me, we are also a collection of particles, right? An organism, a bacteria, virus, a coronavirus, say for example, can it generate a field? So a collection of particles, like a human being or say a coronavirus, can it generate a field? So how can you say? Well, we do know that it is possible to define fields for composite particles. And what do we mean by that? Composite particles, this means particles that are not elementary but are made up of 2 or 3 elementary particles. And the best example is proton and neutron, right? Also we have pions, which are made up of 2 quarks, proton and neutrons made up of 3 quarks. Now these fields are effective fields that may be used to simplify calculations, but they only serve as an approximation to the much more complicated collection of elementary fields that underlies the effective field. Now, anything larger than a composite particle, larger means more than 3, 4, 5, 6, 7, even more than that, is just outside the realm of quantum field theory. So, atoms, molecules, and even chemical compounds may still be described by quantum mechanics, but they cannot be described using fields. On even larger scales, where objects are made up of from huge amounts of atom, even quantum mechanics is no longer applied. And these objects are described using classical mechanics. So they too cannot be described by quantum fields. And obviously, this includes all kinds of organisms, right? Since even the smallest known microorganisms, such as viruses, they contain billions of atoms. Okay, so what do you have to say? So, since my students they don't have any question, probably they are quite stunned by some of the questions as well as answers. So, now let me finally give you a summary of the basic mechanism of quantum field theory. Again, without doing any mathematics. So, what is the basic mechanism? What do we do in this quantum field theory? Well, we do know that fields are the and a quantum field theory is analogous to an infinite collection of harmonic oscillators. Say, for example, there is one infinite collection of harmonic oscillators we call the photon field. Another one is the electron field, and so on and so forth. When the photon field contains n excitations, then we can observe them as n physical photons. And the same argument goes for the electron field as well. The ground state of the photon field is the one where all the quantum numbers are zero. And we call this the vacuum state. And in this state, we can, if you like to detect, then we would detect zero photons, no photons. In every other state of the photon field, some quantum numbers are positive, and it means that we can detect photons in certain states. We can also have superpositions where the number of photons in certain states as well as the total number of photons can be uncertain. So in a way, we can say that the photon has no independent existence from the photon field of which it is just an excitation. The photon is thus a derived concept. I am giving you an example in terms of the photon field. So proceeding forward, we can write down a Lagrangian, of course, Lorentz invariant, right? This is how the field is. So we can write down a Lagrangian or a Hamiltonian for such a field in a way that allows the field to evolve by propagating oscillations. Finally, what we can do is that we can couple that field to the same field or other fields and see that the propagating oscillations have some amplitudes to scatter off each other. These excitations, which can both propagate and scatter, we can think of as particles. And in this way, quantum field theory serves as an accurate model of how particles interact. Of course, if we agree to identify particles with the excitation of the quantum field. Do note that the amount that some fields require more energy than others to create a particle. And so the amount of energy is quite proportional to the mass of the associated particle. Okay. So more or less, I have given you a summary of the various ideas and very interesting topics I have discussed. I've tried to give you information which normally students overlook when talking about this mathematics. Not only students, everyone probably has the urge to follow the maths, to do the maths, and sometimes we often skip out or overlook the basic significance or certain fundamental ideas related to this mathematics. And this I have tried to explain through these lectures. So, any questions, students? Partho, Arundhati? Okay.